Hello, I am Kevin Yu from Virginia Tech. This is joint work with Ashish, Kumar, Budhiraja, and Pratap Tokekar. We look at the problem of multi-robot heterogeneous coordination for persistent UAV missions. Our work is motivated by the use of unmanned aerial vehicles for persistent operations in applications such as surveillance, patrolling, and coverage of environmental monitoring. Persistent missions are typically longer than the standard 30-minute flight time of commercially available UAVs. In such cases, we would like to be able to recharge the UAVs using either stationary recharging stations or use unmanned ground vehicles as mobile recharging stations. The key questions we address is where to place the stationary stations and how to plan paths for the UAV and the mobile recharging stations. In this presentation, we will focus on the mobile recharging case. The answer for the first question of the placement of stationary charging stations is given in the paper. We model the system where the UAVs land on the UGVs, where the batteries then get recharged. The UGV can either stay in place during recharging or can mule the UAV to the next deployment site while recharging. We formally model this problem as a single mobile charging station, or SMCS for short. Our problem takes as input a set of N sites that must be visited by the UAV. There are three types of costs between sites. The problem asks for finding a UAV tour and a UGV tour to visit all the sites without running out of battery life. In the figure, you can see one sample output tour that visits 50 sites. The blue edges are where the UAV travels alone, the dashed red edges are where the UGV mules the UAV to the next site while recharging, and the red edges are where the UGV travels alone. Our objective function is to minimize the total time it takes for the UAV to travel to all sites. Our solution is based on the Generalized Traveling Salesperson Problem, or GTSP for short. GTSP is the generalization of the Traveling Salesperson Problem. The goal is to visit every site on the graph while minimizing the total cost of that tour. In the GTSP, we are given a graph with clusters of vertices, and we want to minimize the cost of the tour that visits every single cluster in the graph once. We create one cluster per site with multiple vertices in the cluster, each corresponding to different battery levels. Once we have formulated our GTSP instance of the SMCS problem, we use a GTSP solver to find the optimal solution. In the end, we get a tour that visits every single cluster with the designated battery level as well as the path for the ground robot. There are three types of edge costs corresponding to the three ways a UAV can travel between two sites. The UAV can directly fly from XI to XJ, in which case the cost is the flight time. The second type of cost corresponds to the UAV landing on the UGV, recharging while the UGV mules it to the next site, and then the UAV taking off at the next site. The third cost corresponds to a UAV landing, charging while remaining stationary, and taking off towards the next site. The algorithm chooses not only the order in which to visit the sites, but also which edges to select between sites. We conducted multiple experiments lasting 20 to 25 minutes each, where the UAV and the UGV carried out fully autonomous missions such as the one shown in the figure on the top right. Instead of recharging stations, we manually cold swap the batteries every time the UAV lands on the UGV. More details are available in the full paper. Our algorithm for the SMCS is publicly available online as well as YouTube videos of full experiments. Thank you.